Good afternoon, everybody. My name is Drew Armstrong. I am the executive editor of Endpoints News, and welcome to Post Talk Live. We are streaming and recording this on June 12, and today we're going to do a deep dive on AI models. One of the really great parts of my job is that every day I get to ask really smart people about their work, and they take time out of their day to explain to me what they do and how they do it. Earlier this week, we had a fantastic conversation with former CDC Director Mandy Cohen. You can check it out in our channel. Today's conversation is going to get into the weeds, and it's happening because, in part, whenever I get on a call with our reporter Andy Dunn and we talk about his coverage of artificial intelligence in biotech, I get really curious and I get also aware of just how little I know. And last year, Andy introduced me to the mysterious Twitter account Owl Posting. Owl Posting is run by Abhi Mahajan. He's a biotech machine learning engineer. He also writes a semi-regular newsletter about AI in biology and lots of other cool stuff. And he's one of those rare voices who can make really technical information understandable and exciting. I've met him for coffee a few times. I wanted to have him on the live stream for a while, and we're finally making that happen. So welcome, Abhi, and thanks for doing this. How this is going to work today is that I'm going to ask some really big, weird questions. Andy is going to pull us back into reality and tell me when I've said something stupid. And hopefully at the end of this, we're all going to be smarter about how these AI models work, what that means for science, and so will our audience. And just as a bit of housekeeping, for those of you who are joining us on YouTube today, you can use the live chat to join in the conversation. You can ask any of us questions. If you're turning late, recordings are going to live on YouTube and on our channel. And if you haven't already, please hit that little subscribe button below and you'll get notifications the next time we have a new live streaming coming up. So welcome. Thank you for being with us. I mean, can you kind of just introduce yourself a little bit? Because you're one of these people who I always I always enjoy talking with, who has kind of a bizarre and interesting and complicated job description, but you've read a lot and you think a lot. And unlike a lot of engineers, no offense to engineers, you talk like a really normal person and are very easy to understand and relate to. So like, what do you do exactly? Can you just tell us in terms that I'll understand, and then we can get into the terms that I won't understand?
Yeah, right now I am in between jobs, waiting to start my next one. But prior to that, I was a machine learning engineer at Kind Therapeutics. That company is a Church Lab spinoff, founded on this idea that you can mutate AAVs, which is the genetic delivery mechanism by which you can insert extra chromosomal DNA into cells. Part of my job there was building up infrastructure at the company to train models, a few research projects to actually create better viruses in the first place, and various other engineering tasks. Prior to that, I worked in clinical informatics at a healthcare insurance company, just writing papers, trying to make something useful out of the 50 million claims data records we have. Um, and right now I write about biology, machine learning, and uh, yeah.
Okay, got it. I think one thing that, I think I have talked with Andy a little bit about is I use AI models, like you would expect someone who comes from a writing and editing background would. I mean, I'm very much engaged in kind of these language-based models, ChatGPT and things like that. And I read Andy's writing and I talk to people like you about, some of the work they do. And I think I can, it's very easy for my brain to conceptualize, I think, what these, language and language interactive models do. And I think I really only have a much more abstract idea of what some of these, biological models do. Can you kind of explain it? Like, how would you explain to somebody like me the difference between these things, for those of us who either write about this business or work in this business and may not have really gotten into the weeds with some of the tools that people like you use?
To some degree, a fair number of the biology models I can think of operate, at least on the machine learning side and the theory side, on a pretty similar level to what you would see in the image and language space. Diffusion models in the protein modeling world are like denoise three-dimensional coordinates. In pixel space, it's denoise pixels. Or and similarly for uh, language modeling, there are models in the protein world that iteratively mask out sections of amino acids and try attempt to refill those in. Similarly, in the natural language space, you mask out sections of words and attempt to fill that in. Like the one difference there is for proteins, there's no natural ordering. With language, it goes like from left to right. So you can iteratively demask in that way. But for proteins, it's kind of all, it doesn't really matter how you demask. Similarly, for like the cell phenomics space, where you're dealing with microscopy images, again, like it's not too dissimilar to just dealing with normal images. As such, like a fair number of the methods that you see in the typical machine learning papers at like our NeurIPS, ICLR, et cetera, there's like a pretty like good level of translatability between theory in that field and theory in this field. I think there are some people who have said explicitly that this is a bad thing and that there is like a new set of theory that should be built up within the biology field because biology has its own unique set of priors that don't exist in natural language or images. I think one interesting example of this is for like single cell RNA foundation models. I think a lot of people are finding that they don't actually do anything. They aren't actually telling you any more interesting information about the world than just like the mean gene counts amongst this population of cells. And because it's really great founder who I'm going to name drop, Adam Green at Markov Bio, who has kind of said that it is because people are not, or people are like straightforwardly using the loss functions from the pure ML world without actually thinking about how like real biology is working and attempting to create new ML theory from scratch with that biology theory in mind. Long-winded answer. I'm not sure if I answered that fully.
Yeah. I guess like one of my questions, and I think part of the reason prompting for this conversation is like I feel like I have a very good conceptual human understanding about how a written language model that I would use, that I might use, would work. Like I can understand how that thing might think because its inputs and outputs are essentially identical to like, how I perceive the world. And I guess another question I have for you, and related to what we're talking about, like, does that type of, logic still hold in when we start talking about, different types of data, biological data and things like that?
Sorry, could you expand on the question a little bit more?
Yeah, I guess like
maybe I'll jump in.
Yeah.
Like, let's see. I'll see if I'm like feel free to if there's something to add to this too, Drew. But like, I guess the idea of like explainability and interpretability of models of like the natural language element. I think that's something that I've kind of seen a little bit in some of the like the AI bio models is playing around with like, do you gain something from that? I mean, there's a bunch of questions in there, but I guess I'm wondering overall how you view that.
Like, is the question over like whether the mechanistic interpretability stuff is really affecting the biology models all that much?
Uh, yeah, I think that's part of it. I think also is like at a basic level, if you add sort of natural language into some of these models, is that helpful or not? Or I guess to really step back, do we need to know what these models, how they're thinking, how they're reasoning?
Gotcha. Yeah.
Yeah.
I mean, yeah, where is the field on
Thank
that?
you,
And just like
Andy,
your
for
own
putting
thoughts.
this in clearer terms than I
Yeah.
have. Yeah.
This stuff is very
I said this was
jargony.
going to happen. So
Yeah.
I think a good way to think about maybe perhaps all of biology is that the real fundamental truth of the whole system is physics. So it's physics all the way down. Um, and so you can think of like the first people who were really trying to computationally simulate biology were physicists building molecular simulation programs where they build up proxy versions of true physics and use that to like guide these like ball and spring models that they created. Um, Over time, people eventually realized that. So you can kind of think of like that's the base layer of everything. Physics is the base layer of everything. And now you have the resurgence of neural network potential models that try to create machine learned analog physics, something that tries to have some conceptual understanding of like long range electrostatic interactions between atoms, something that has some conception of like conserved potential energy of the system, and so on. So like again, it's still explicitly paying attention to the physics part. One layer above that are like stuff like AlphaFold 2, where it is trying to learn some mapping from amino acids and like multiple sequence alignments to structure. But to do that, it's not learning something fundamentally new about the universe. It is still relying on some proxy of physics combined with some like prior it has based on like evolution. Because you can imagine that like if two residues are evolutionarily conserved across the entire tree of life, that probably means they're like interacting in some capacity. So they're probably close to each other. And through this like like and so like again, like probably at the like very most top, you have things like natural language protein models, which don't even pay attention to structure at all. And just hope to learn all the information you could ever want purely from the amino acids. Uh, and again, I think like throughout all of this, we're in some sense dealing only with proteins. But the same thing applies even if you look at these larger phenomics models that operate off of pathology slides or microscopy slides. You can kind of think of that as almost like an extremely coarse-grained physical simulation of the world. Just like a such large layer of abstraction that you no longer care about, or you're not explicitly modeling individual biomolecules, but rather cells in their immediate environment. But again, all of it is just physics. You're not learning anything more than just physics.
I'm going to try to ask another question here based on some of this answer, and I might rely on Andy to once again save me. But I think, when we think about, the world of biology and the world of physics and how these models work in terms of being able to make predictions, how much of a problem is it that like there are vast parts of biology that are unknown? I mean, does the physics, does what we know about physics let us kind of bridge across these unknowns, versus saying, hey, there's a lot of holes in our knowledge, or we have to go and do experimentation to figure these things out. Like how much of an issue is the kind of the vast unknown of how biology and all these other things work? Or is it that we can be, the physics are good enough that we can be really predictive and fill in lots and lots and lots of blanks?
Yeah, I think at least if you look at so obviously like something like trying to simulate true physics as a molecular simulation is obviously intractable. So we need to look at something higher up the abstraction chain to see if it's useful enough. And the next layer up is like these neural network potentials. And so one question we can ask is, are these neural network potentials capable of modeling all of biology, all of chemistry? And the answer is probably not. But for all intents and purposes, that may not matter because the
Okay.
slice of biology and chemistry that has to do with like human physiology and human health is probably enormously small. It's a very small fraction of the true chemical universe. And even if your model is only capable of understanding that system and that system alone, it's potentially good. But you could go one layer deeper and say, well, perhaps I can understand like this discussion of perhaps like stuff like AlphaFold 3 can model proteins found in evolution really well, but can model like de novo proteins that have like never that have no real homologue to anything that exists in nature. And I think that what's turning out to be the case, and I'm actually not 100% sure about this, but I've seen some results that suggest that the larger and more sophisticated that these models get, the more that they're incapable of modeling this like set of non-natural proteins, because the fitness landscape it's being trained on are natural proteins. So the more it's able to approximate that space, the worse it gets at approximating or at extrapolating outside of that space.
Okay.
I'm not quite sure what the solution is there. And like the solution may very well be to add in some physics, because physics is always true no matter where in chemical space you go. So the end state of all these models will almost certainly be a combination of physics to like help guide guide the simulation process, and then machine learning to take it over at the end, or like inverse. I'm not entirely sure. I think an argument can be made for either way.
That's super, super interesting. Another question, and I asked you this when we met for coffee, and we talked a little bit about this. Is like, and again, I'm going to misstate things. I fear, but you know, you had mentioned this idea that some of these models, like, we are less and less able to kind of understand the reasoning path by which these models come up with conclusions. Can you talk about that and kind of explain what that means and what the implications of that are? Have I prompted this topic correctly?
I guess we have some fuzzy insight into how they work. Uh, when like AlphaFold 1 came out, and even AlphaFold 2, a lot of biologists wrote it off as this is just glorified homology search, which is like trying to find like you try to find other proteins that have been experimentally characterized, and you just try and like approximate the structure based on like previously determined structures. And to some sense, that is true. AlphaFold is really a glorified homology search combined with some level of physical minimization on top. And as is EvoScale or evolution or like the ESM models that Meta released. Um, I think we understand that. What we perhaps don't understand, I think, is like neural network potentials. What exactly is that learning? What slice of like force fields is it able to capture such that's able to like get to DFT level accuracy or like density functional theory accuracy without needing to go through the math of actually getting there? Um, I get like the answer is like almost like it depends. It depends like which layer of the abstraction tree you're talking about. There are some areas where the answer for why is it coming to this conclusion is something we very clearly understand, but there are other areas where we don't understand it at all. But we also probably will understand it within the next 1 to 2
Got it.
years.
Do we need to understand those things? I mean, I guess like how helpful is it and in what context to have that understanding?
Yeah, I asked Sergey Ovchinnikov, an MIT professor who's like really probably like the goat of the field, in a recent podcast about this. And in his words, it's something like the biophysicists really care about understanding how these models work, but it's more of a question of like intellectual satisfaction for them rather than it being absolutely necessary to understand how like what's going on. Because to some degree, we don't know how a lot of drugs work and they
Yeah.
still manage to do their job perfectly fine. And the same will be true of these models and the outputs that they produce almost certainly.
Right. Like, I mean, if I'm a research scientist using this at a drug maker, like, is it okay for this thing to occasionally be like a magic black box for me?
Yeah, I think so. I think like
That might not be a very satisfying situation, but like,
yeah,
you know, like if this is a
I yeah,
tool, do I need to know how the tool works?
I think see the degree by which it makes people comfortable using the tool is almost the only part that matters. With regards to like, do we truly, genuinely understand what's going on in this black box? I'm not sure if we'll ever get there. I think there's a good argument that can be made that almost every model that reaches a certain level of complexity, whether that is in how much like flops it took to train or how many parameters it have, quickly gets beyond the scope of any one human to actually understand what's going on. Um, like even like to some degree, even like the sum total of human biochemical knowledge is really deeply understood. Like you see these like really large biochemical maps that Merck has put out to hang up as a poster in your house. And it's like cool that we know all this information, but like no no biochemist is actually walking through all of these maps to come up with their drug. They're usually focused on a few pathways of interest and like just like focus in on that and kind of ignore everything else and hope that if it does impact something else on this pathway map, they learn about it incidentally, but they don't care about it to start off with. And the same will likely be true when people use these models in practice.
It also kind of feels like I wonder if you agree, disagree with this, Abhi, of like more task specific models. Something like AlphaFold is just it's very specialized. It's not like this big general model of if you think about like an LLM, it can do tons of stuff. AlphaFold just does biomolecular structure predictions. I don't know if you really need to know the reasoning, right? Of like it's either right or wrong on the structure prediction, and you can find out like in the lab. And then I think there's some level of like reliability scores it can also put out, which is kind of interesting. Of like maybe you do want to know how it comes up with the reliability score,
Mhm.
because like if you start trusting stuff to replace experiments, that's where you probably need to know that, rely on it a bit more. But I guess I'm wanting to extend that maybe of like to speculate wildly into the future. One, I want to know if you think this is a buzzword or if this is like a helpful phrase of scientific superintelligence. I feel like there's a lot loaded in that.
Mhm.
But yeah, is there a helpful definition? Have you thought about that idea? Is that a legitimate goal or is that more just sort of marketing hype? uh, of, some long-term idea here?
I think I don't know. I think it's like just to some degree, no one has the correct answer to this as of yet. There's a lot of scientific superintelligence startups that are spinning up, and I don't really have a good sense that any of them also understand like whether they're like what scientific superintelligence will actually look like in practice. I think the bet that the answers are all out in the literature, and we just need to synthesize them and combine them together in some very specific fashion to come up with interesting hypotheses. I think is like true to some degree, but I think it's going to be a lot less transformative than what people suspect. I think humans are actually quite good. Like if you have like these millions and millions of postdocs and PhD students and professors all like teaming through the literature to find something, I think a lot of AI people look at that and think, surely humans aren't very good at this problem. AI could come in and do it better.
Yeah.
But I haven't really seen strong evidence of that yet. And maybe that will change in the next year or so when Future House announces something really crazy. But at least for the moment, it feels like the normal iterative process of a human sitting down and thinking and going through the literature themselves and thinking again seems to work quite well. And
What did you make of Future House's release, by the way? Because
I
they
think
released
they
some
like,
sort of scientific research tools for our audience that
yeah,
I think, free for everyone, where you can go and play around with them too. But yeah, curious to your
yeah.
thoughts on it.
But yeah, it currently is free. They do have a rate limit. I use it quite frequently. I think it is by far the best like deep research-esque tool that is out there. Um, Purely because I think it's like much better at like one, like good at being pretty succinct, and two, much more attuned to the literature than I think other tools are. Their recent release was this discovery that this particular drug is really good for, I think, wet AMD or dry AMD. I forget the exact one. And then a bunch of people commented that, oh, there's been other papers that suggested it's really good for dry AMD before, or wet AMD, whatever like the inverse of what they suggested it was. And then other people said, oh, but dry AMD and wet AMD are actually quite different diseases with like very different therapeutics used for them. So maybe this is potentially interesting. But at the end of the day, no one has actually confirmed whether this drug is useful for the thing that Future House recommends it is. It's kind of just the tool has really good evidence, so we think it is. I think up until we get to the point where someone directly takes an innovation produced by one of these tools and turns it into, at the very least, an IND enabling drug, uh, I would be a little bit hesitant to really like at least like bet my house on any of that work. Um, I
Yeah.
think like for at least like AI and drug discovery, like you're kind of seeing these early reports of how like there is like phase one improvement rates are like getting higher due to AI. There was that one consultant report. I'm not sure how much they actually even trust that, but there's like on the face value, it does seem to be being useful there. With these AI superintelligence tools, I think we're a few years away from actually seeing the results of it.
Yeah, I like to vastly oversimplify, and this is like a joke I feel like I've made several times at Andy. Like, I feel like on the one hand, you have this debate of like, this is going to be like Excel, like this will be a boring tool on a computer. And then on the other hand, you have people being like, when are we going to get rid of all these scientists and just use this? And like, obviously the truth on this feels somewhere in the middle, but I'm wondering if you kind of lean in one direction or another. I suspect you're very firmly in kind of the middle of that extreme wide that set of enormous extremes, but how you think about these tools and their true kind of, will they be truly revolutionary in how we do science or what it means to be a scientist at a drug company in the next few years?
Yeah, I mean, obviously, like in the maximal case, of course, like 30, 40 years down the line, AI probably will be doing everything, including writing my articles. But at least in the short-term case, I don't imagine that. I guess like when people think of scientific superintelligence, they think of a tool that can just like sit in a box and theorize to itself and come up with the answers to all of our solutions. And that might be true in cases where like your main bottleneck is like being able to physically simulate the world. Um, like I can imagine this being true for like ML. So like there's a lot of ML in like autonomous research companies that are able to produce papers that are entirely written by AI. and are at least good enough to be accepted by really good conferences. I think there was one at NeurIPS, there was one at ICLR. Nothing as of yet has happened in biology, and I think the reason that is biology isn't quite leaky in the same way that a lot of other fields are. Like if you look at machine learning, you can kind of look at like one method there, diffusion, and say like, oh, diffusion is actually spectral autoregression, and spectral autoregression is actually something else. Like all the math kind of collapses down to like was like somewhat fundamentally the same thing. I don't think the same thing is true in biology, where there are a set of rules that were dictated by someone who is not us, and it's up to us to like iteratively learn those rules via wet lab experimentation. Like if you had a super intelligent sit in the box and ask it to come up with a definition of like VDJ recombination or what like an immune checkpoint blockade would look like, it would not be able to come up with that because it doesn't have the necessary almost like semantic tools to even reason over that. Um, Once you pair up these super intelligences with access to like wet labs or access to be able to like inject that stuff into in vivo systems, maybe you get something really crazy. And that's what I think like will happen in the long term. But as of now, I think there's like a lot of companies which claim to have this like iterative, like tight feedback loop between
Mhm.
like the AI super intelligence and the wet lab. In practice, I think it's somewhat similar to the like the early days of AI, where AI is potentially being helpful to some capacity, but there is a pretty strong human in the loop component.
Well, on that, because I think that's super interesting when I like think of like the sci-fi-esque future for this space of like autonomous science. And it is really interesting to like think about. I haven't, someone email or text me if you have seen this going on of like a company or organization really trying closed loop science in the way of like put AI at the center, generates hypothesis, and it has access to what you're saying there, Avi, of like the physical tools, like something like an intelligent enough robotic arm in the lab to run the experiment it wants to run, get the results, like keep going around the circle in itself. And I thought I wanted to ask on that of like this is like kind of contrived, but like it kind of two paths for the future here. If you see AI as more like the captain or the co-pilot in science, because I think captain would be more the philosophy of it needs to be at the center. And if it's the captain, it's probably going to fly the plane in a radically different way than humans have ever done it. And we won't know why it's doing what it's doing. But it likes, it's on to something or wants to try that, right? And then
Yeah.
like co-pilot is more where with the humans in charge, we still believe in like eureka moments and science and serendipity and that you grind it out in the lab, right? That is still the core element. And these are really helpful tools. Does that make sense as far as, I mean, two
Yeah.
ways this goes forward? And what do you think of both of those?
I I think that is a good way of looking at it. I think an even more grounded way to look at it is how long can you leave this AI alone before it has to be interrupted because it's finally gone off the rails in some capacity.
Yeah, just
And I
into
think
gibberish or some type
yeah,
of weird loop. Yeah.
and like one way you can kind of conceptualize the impact of AI that AI will have in any field is to look at the field where it's being deployed the most heavily with the fastest feedback loops, which is software engineering. And right now, like OpenAI Codex, Cursor, like et cetera, is all pretty good, but they cannot run interrupt uninterrupted for like hours on end and build an entire product from scratch themselves. If it cannot do what is like a relatively simple task there for hours on end, it feels like a stretch to think that it will ever be the captain of like a lab and be able to just spend tens of thousands of dollars on reagents when it doesn't like and then like it fails to use them at all. Um, I think the second you see this like ability to stay consistent in its reasoning traces for days on end in other fields that have these much like tighter feedback loops of like reward and like not reward, then I think you will have the hope of seeing that in biology. But up until that happens, I'm relatively skeptical that there will be this like AI as captain. Copilot feels like a much stronger use case in the short term.
You just brought something that I'm really curious about. Like when we think about like these tools and using it on a coding capacity, like how much smaller is that world of coding than the world of biology? Because I have to imagine, while it's complex, like as a system, you know, code written for a software program, like it would be, like the head of a pin compared to a lot of what's going on in biology. Am I right in thinking about that as like, you kind of alluded to this as like, these coding tools as being like relatively self-contained and small. Is that a right way to think about this in comparison to the much more kind of open, free-form world of human biology or animal biology?
I think there's obviously a spectrum in both cases, right? In biology, there are like well-developed protocols that like doing PCR or something in undergrad in biology could do perfectly by themselves, whereas like like mass producing viral capsids at an economic scale is something that's quite challenging to do. One requires relying on like thousands of pages of literature that have been developed in the past, and the second requires like developing brand new systems, buying brand new tools that potentially haven't been created before. A similar case is probably in the software engineering world, where there are things that there's a lot of pattern matching that can be done in the software engineering world that these models are really excellent at. But the harder stuff of like, um, I want to like distribute this training process in a really strange fashion across like heterogeneous GPUs. I wanted to like shard in this really weird way that has never been like laid out in the documentation before. Stuff like that it does decently well at, but still obviously not perfect. And I imagine it will be somewhat the case in uh in biology as well. And so, okay, in software engineering for like when you're developing a project, it will during its life cycle have both easy and hard aspects to it. Similarly, when you're doing any sort of research project in biology, it will also have this segment of easy and hard segments. And up until an AI is able to reliably do both of those sections without being interrupted, it's unlikely it'll ever be the captain of either. Um, it feels like we'll get to that part much faster in software engineering than we will in biology.
Is part of that on that the idea of like, because I know nothing about coding, but I'm at it's like we made a humans made up that as a language, so that feels like kind of I think Drew is getting at that of like define pro like there's only
Yeah.
so much code like we created the rules like a machine should be able to intuit all the rules that we created because we made them, and like biology is fundamentally a different beast there.
Yeah.
I guess on that on the bio side, what you see as like the bottlenecks ahead of maybe to go a few layers deep here, I think everyone agrees that data is a huge part of it, and that we don't have enough data, and then we're not able to generate enough data. But I'm kind of most interested one layer down your thoughts on like we don't even know what type of data we need to generate, if that makes sense. Like are we collecting the right types of data? And this kind of is a very circular way to get back to we just need like better methods of actually like observing biology in new ways. I don't know if that makes any sense to you.
Yeah.
If this relates to like also getting at the idea of like we really need data sets that shed light on like causality of stuff and not just allow for like correlations, which work a lot better in languages.
There was this really interesting paper that came out of Bo Wang's lab at University of Toronto, I think a week ago, called BioReason, where they paired up a DNA language model with Quen, which is I think a Chinese language model, and taught the this language model to have like reasoning traces that interpreted the DNA directly. So like the DNA language model was in charge of creating like some latent space of the DNA that got fed into Quen. Quen ingested it, learned like was given question answer pairs that laid out a reasoning trace, and like was able to like improve upon the state of the art in some capacity. And one really interesting thing there is that the reasoning trace that this model was trained on was not trained on like clinician or geneticist created reasoning traces. It was created by giving pathway information to Claude 3.7, Claude generating a potential reasoning trace, and then Quen being trained on that. Um, so there's this potentially interesting idea that like natural language LLMs already have this like fuzzy understanding of biology, and you can kind of use that to bootstrap your way up to something that can operate off of like pure raw DNA without having to have this intermediate language model.
Abhi, I want to ask you, when you're thinking kind of about, what are the really big problems out there or kind of compelling next things? Like, what are you looking for that's going to make you? And we talked a little bit about this, like, hey, can this thing run for hours and hours and hours on end? I mean, what are you looking when you're thinking like, oh, like the next big breakthrough that would be really cool if someone did would be X? Like, what do you think is going to be, what do you think for the signals are going to be the signals that this field is really making progress or that you're looking for? And I hate asking people to look into the future, but I'm going to ask you to look into the future.
Um, I think again, like I kind of view the state of natural language machine learning as a lagging or as like a future indicator of where biology is going to go. So the second, um, well, what's a good analog? I think the second you have like a purely AI written paper over some novel biological concept that can be like, accepted at a really good ML conference, that's probably like a good indicator that there's like something going on here in the world of scientific superintelligence that would like probably like should make you think like should I join one of these companies? Um, I think another indicator would be that we get really good models of in vivo systems that are able to generalize pretty well across like vast swaths of chemical space. So there's this like to just like name a startup, there's like Axiom, which is trying to develop these like hepatocyte toxicology models. And so without having to do the actual wet lab process, you can just rely on purely these assays. Right now, I think it's like I don't think they've released anything official as to like how successful they are at this. I think the second they're able to confidently say that you can skip this part of the preclinical or clinical development process, and you don't have any you don't have to have any fears that you did anything wrong. We have like a nearly 100% success rate. Then I think that's like a strong indicator that something crazy is about to happen. And to some degree, that was the marker that like AlphaFold 2 met. Like you don't need you could crystallize something if you really wanted to. If you don't, if you're working with a really strange protein that you suspect AlphaFold, it's not going to work with. But in most cases, you no longer need to experimentally determine things. You can rely on AlphaFold for a pretty good approximation of what's going on. If we get to that point for more complex problems outside of the space of a single biomolecule, then I think it feels likely that like something interesting is going to happen there, but I'm not entirely sure in what form it will take.
Well, I could listen to you explain things and then realize I understand maybe 50% of it, but I'm captivated by it anyways, all day long. But unfortunately, we are out of time. Abhi, thank you so much for joining us. You can find him on Al Posting on Twitter or on Substack. I wish more people who work in science and engineering wrote and did work like you do. So thank you for doing all that. If you have a great idea for a future guest, tell us. You can find our email addresses on endpoints.news and write us. The recording of this conversation will live on YouTube. If you want to have feedback for us, please send me a note. I love hearing from you. As a reminder, if you are already signed up for our post hoc email newsletter, you'll get notifications when we have a new broadcast coming up. If you're not signed up, head over to endpoints.news, go to the top right-hand corner, hit the reader profile link, then preferences, and you can activate post hoc to get notifications. You can also follow us on Twitter, X, LinkedIn, YouTube, and Blue Sky by searching for Endpoints News. And soon we're going to be launching our product on podcast platforms as well. Thank you very much to our producer, Nicole Wetzman, our engineer, Dalen Turk. Both of them may make this whole thing happen. We will see you the next time news breaks.